So here's an example of the theorem that says your ideal is maximal if and only if your polynomial is irreducible. So here I have a field, Z2. So I'm going to look at polynomials with coefficients in Z2, all operations done mod 2. And here I have a polynomial. The polynomial is x squared plus x plus 1, and I claim that's irreducible. It's irreducible because it's a degree 2 polynomial that does not have a root. It's degree 2, and it does not have a root in Z2. If I plug in 0 into this polynomial, I don't get 0. And if I plug in 1 for x, I don't get 0. So it's an irreducible polynomial. That means this polynomial, this ideal is maximal. And when you form the quotient ring with a maximal ideal, you get a field. So here's an example of a field, and I want to write down what elements in this field look like. So elements in this field are 0 plus your coset, 1 plus your coset, I think you could also get x plus your coset, and lastly, x plus 1 plus your coset. These are the 4 elements in your field. Now, why are those all the elements? Let's look at the coset x squared plus my ideal. Why isn't this a new element? Well, look at what you could do. Every time you have a degree 2 polynomial or higher, you can do this. You can rewrite x squared as x squared plus x plus 1 minus x plus 1 plus your ideal. So I added and subtracted x plus 1. Now, this term is in my ideal. So that could be absorbed in there. That's like a 0 in this ring. So the only thing I'm left with is negative x plus 1. Now, since I'm in Z2, negative x is the same as positive x. So I get x plus 1 plus x squared plus x plus 1. So x squared plus my ideal is actually the same coset as what I have over here. So these are the only 4 elements in my coset. Why? If I have a degree 2 or higher, I could always reduce it to be a degree 1. And these are all the degree 1 or less polynomials in Z2. Now, let's do the multiplication tables. So let's do, so I don't have to keep writing these down all the time. Why don't I call this equal to 0? I'll call this element 1. I'll call this element alpha, and I'll call this element beta. So let's do the multiplication tables. First, the addition. So I have 0, 1, alpha, and beta in my ring. It's actually a field. If I add 0 plus anything, I get back what I started with. 0 is the additive identity. If I add 1 to itself, so 1 plus 1 in Z2 gives me 0. In fact, since I'm in Z2, every element is its own additive inverse. X plus x is equal to 0. So alpha plus alpha is 0, beta plus beta is 0. 1 plus alpha, so if I do 1 plus alpha, I get beta. And if I do beta plus 1, the plus 1 and plus 1 adds to 2, and then 2 and Z2 is 0. So this gives me alpha. And you could fill in the rest of the table if you'd like. I think this gives you beta 1 and then alpha 1. So this, we could see, shows that the field, let's call this field F so I don't have to keep writing it down. F with the addition operation is isomorphic to the group with 4 elements, every element its own inverse. That's Z2 cross Z2. What about the multiplication? This is a field. So there's an addition and a multiplication, and the multiplication is commutative. Every element is its own inverse. Or excuse me, every element has an inverse. So let's write down 0, 1, alpha, beta. 0, 1, alpha, beta. Well, actually, 0 does not have a multiplicative inverse. Every element except 0 has a multiplicative inverse. So 0, 0, 0, 0, 0, 0, 0. Now, 1 is the multiplicative identity. So I get 1 alpha beta here. Now, what happens if I multiply alpha with itself? So what is alpha squared? Well, alpha squared would be x squared plus my coset. And over here, I think I calculated that you get beta. So alpha squared is beta. And alpha times beta, I think you could prove, gives you 1. So 1 means that alpha and beta are multiplicative inverses. Beta times alpha is 1, and then beta times beta you could prove is alpha. So the field with multiplication, actually I should throw away the 0. The field without 0 and multiplication forms a group. That group is isomorphic to Z3.